Is Albert Atserias from Barcelona, and he's talking about indistinguishability in counting logic and the complexity of semi-algebraic proofs.
Thank you. Welcome everybody, and thanks for waking up at this time in the morning. So this talk, I was told that this workshop was going to be about mixture of people in finite model theory, descriptive complexity, and proof complexity people, and also bounded arithmetic people. So I managed to put in my title two concepts, one from descriptive complexity and one from proof complexity. I didn't manage to get bounded arithmetic also in the title, but so this means that the talk is going to be a bit a mixture of these two topics, and I will try to discuss a little bit each of them. So I will start with some overview of descriptive complexity. And so what I want to do here is to explain a little bit what the main problem is, the problem of the logic for p-time, and how I see it and why I think it's important. And on the way to that, I will introduce some logics that will appear later in the talk. So the general picture that we have is the following. We have first order logic on one side, and we have second order logic on the other. We could have higher order logics, but let's stop at second order logic. And then in the middle we have some fragments of second order logic, such as sigma 1, 1 and pi 1, 1. And of course these are subsets of second order logic. And first order logic is subset of these two, but in the middle we usually put some other logic, like here I would call it inflationary fixed point logic, or least fixed point logic, some people also use, but it's essentially the same logic, I mean, with some difference. And the aim of this hierarchy is to capture complexity, as in the complexity hierarchy. So in the complexity hierarchy, what we would have is that for second order logic, this would be the polynomial time hierarchy. For sigma 1, 1 and pi 1, 1, we would have NP and co-NP. For first order logic, we would have AC0, complexity class AC0. And then, of course, we want to have also P in the picture for polynomial time, which would be subset of NP and co-NP. So this would be the complexity, the classical complexity hierarchy, and this would be the descriptive complexity hierarchy. Okay, so the question is, what is this correspondence exact? And well, it turns out that if you look from this point onwards, then the correspondence is exact on any class of structures. Correspondence exact. By the way, I'm talking about finite structures all the time. Maybe I should have said that earlier. Usually sigma for me is a finite relational vocabulary. And relational means you have relation symbols, no function symbols, maybe constant symbols. And then my classes of structures are always finite structures. In this talk, there's not going to be infinite structures. Class of finite sigma structures. So if you want to fix your mind, you can think of this finite relational vocabulary to be the vocabulary of graphs, and we're talking about finite graphs. All right. So as I was saying, this correspondence between descriptive complexity and classical complexity is exact, holds exactly on any class of finite structures. I don't say finite again. And what this means is that everything computable, if you fix a class of finite structures, say, I don't know, bipartite graphs, and you look at the properties that are computable in NP, the properties of bipartite graphs that are computable in NP, then these are exactly those that are definable in sigma 1, 1. And conversely, and this holds for all the classes here, while this correspondence here is not quite exact on all classes, but it happens to be exact if the structures carry enough arithmetic in them. Correspondence exact only if structures carry arithmetic. And by arithmetic here I mean, well, the linear order as a minimum, linear order on your universe, which you can think as natural numbers from 0 to n minus 1, but then maybe possibly also plus and times. Sometimes this is necessary, sometimes it's not. For example, for this with the linear order it's enough, because once you have a linear order you can define plus and times. But for this class you better put plus and times, otherwise the correspondence is not exact either.
So you mean only if really or if?
Hmm?
You mean only if really or if?
If, actually. Yeah. Thank you. But this was natural language, not logical language. On the other hand, if you don't have...
Those two particular examples only if also.
No, but it's, I mean, it could be that you put other other things and it still captures. Up to definability, then it's only if, also in this case. Anyway, so now at this point you might ask, from someone coming from bounded arithmetic, the question is, okay, so if you have arithmetic, then just throw it in, and why should we bother to not throw it in? While in descriptive complexity we look at what happens if you don't have this and what classes you get. And so someone in bounded arithmetic, for example, as an example, would maybe stop listening if I stop dropping these things, right? So let me motivate a little bit why we want to think of this if I drop this arithmetic, and why this is still interesting question. So maybe I should say what inflationary fixed point logic is, just as a reminder. Well, first order logic we know. In first order logic we have the sigma atoms, which in the example we have in mind is just edge relation and equality, and then the usual things. In inflationary fixed point logic, what you try to do is to enhance this logic by some mechanism to include some recursion, some inductive definitions. It turns out that this is quite weak, as doesn't have much of expressive power, essentially because it belongs to AC0. So if you want to go further up in the hierarchy of complexity, you have to add some mechanism to do some computation, and inflationary fixed point is that. So the idea is that you have a formula with some free variables. So this is a set of k free variables, and this is a k second order relation. This is first order variables, and this is second order variables. Now this on every structure, this defines an operator on, let's say, the universe. Let's call it M. So it's m to the k into m to the k. So it takes subsets of m to the k and maps them to subsets of m to the k. And the way this operator is defined is that it takes a set A and it maps it to the set of tuples in m to the k, such that m models this formula when x is replaced by A and R is replaced by capital A. You do this and you include A already in it. Okay, so from A you go to A plus the things that are satisfied by this formula when you plug A inside the R. So this defines an operator, and this is a monotone operator. So in particular it has a fixed point. So now what you do in this logic is you add a new formula, IFP of phi. This is going to be a new formula that will have free variables x, and the meaning of this as a definition in a model M, so M satisfies this if and only if x belongs to the least fixed point of this operator in the structure M. So let's call the least fixed point, I don't know how to call it. Yeah, so let's say the minimum R such that phi M x R is equivalent to R. Right? This is just the fixed point of this operator, and this is a new formula that you form. All right, so this is inflationary fixed point. You might have seen least fixed point also, and least fixed point is just the difference. The only difference is that you start with an operator that is monotone, and then you don't add this thing, but it doesn't really matter. The logics are equally expressive by actually a result of Gurevich and Shelah in finite structures and by Stefan Kreuzer in general structures. All right, so we have infinitary fixed point and inflationary fixed point and first order logic. And now let me give some examples of definability here. So for example, now once you have these operators, you can define connectivity of graphs without any problem. But you can also define polynomial time complete problems, such as the circuit value problem. So here in this problem, you're given a circuit encoded in some way as a relational structure. You're given an assignment to the variables in some way, as a unity relation usually. And as an inflationary fixed point formula, you can define all the intermediate values of the circuit and then the output also. So, and this is a P-complete. So this means that this language is expressive enough to capture polynomial time complete problems. But let me also give some non-examples which are quite dramatical. So a non-example is, for example, you cannot say whether the universe of the structure is even. So this is quite dramatic in the sense that it's such a basic thing that should be expressible by any logic that supposedly captures P, but it doesn't. It doesn't. So, and therefore there's been some attempt to try to enhance this logic a bit more by adding some counting, and I'm going to discuss this later. But at this point, I still want to discuss why do we want to drop this arithmetic, because if you had this arithmetic, then the evenness of the universe would be immediate, right? So the question, the leading open question of descriptive complexity is the existence of a logic for P. You can ask the following. So logic for P problem. Is there a logic, and this has a formal definition, that captures P on any class of finite structures? And here there are two things I would want to have to define, which is what is a logic and what is captors. But we'll just give it by example, just as NP has one. Okay? NP has one logic, which is sigma 1, 1. This is Faken's theorem. So think of in what sense you mean that sigma 1, 1 is a logic capturing P, NP, and then you want the same thing for P. So definitely inflationary fixed point doesn't, because of this thing. Now, okay, so back to this idea of why would we drop arithmetic. So you should think of the origins of the question. So if you focus also at this level, you could ask the same question. You could say, is there a logic for AC0? And the question is also open. It's not known. FO is definitely not a logic for AC0 if you drop the arithmetic. But the question here is a bit more fishy, because there is no clear argument why AC0 would be a more natural complexity class than FO. After all, AC0 is also quite a weak complexity class. It cannot say that the number of edges in the graph is even, right? AC0 cannot do that. So it's a bit fishy to say that this is a more natural complexity class than that. And in fact, in certain contexts, like in database theory, it makes a lot more sense to consider this as your basic complexity class, because in database theory, what you want to do is to be representation independent. You don't want to depend on how the structure is represented. You don't want to depend on how the database is represented in memory. So you want to be representation independent, and therefore you have to drop this kind of, especially the linear order, which is fixing some order between the elements, and therefore is giving you some more information on how the database is represented in memory. So in certain contexts, this class is actually more natural than this one as a complexity class. And it's not clear that this should be the right one. Actually, the definition of this is not the cleanest. If you think of uniform AC0, it has quite a complicated definition. Now, on the other hand, if you're still in the context of database theory, then it's a very honorable goal to say, okay, can we come up with a query language that captures all polynomial time properties of your database? And in that context, I mean, it's pretty clear that polynomial time is a natural class, I mean, by now at least. We understand that we want to capture polynomial time, but we would like to do so in a representation-independent manner, and therefore comes the question of the logic for P. So is there a logic for P that is representation-independent?
So you say that you have this nice correspondence if you have arithmetic, but you don't have multiplication in AC0. So what does that mean for O in AC0?
Now, this multiplication is on the elements of the universe, which are small. So these are log n bit numbers, and that multiplication you do have. So this
Isn't database always ordered?
excuse me.
Isn't database always ordered by some physical?
Of course, it is ordered, but your query language should not depend on the order. The query language you want to be based on the semantics of the database, not on the representation of the database. So you want your query languages to be semantic, but semantically based, not syntactically based. So in fact, this logic for p-time problem comes, first formulation of this problem comes from database theory. This was by Chandra and Harel. And in the late 80s, 70s or 82, thank you. And then later it was formalized also by Gurevich a bit later. All right, so this from this database perspective. But then you can also think from the computational complexity perspective, there is one interesting question, which is, well, there is a logic for NP, Fagin's theorem, in the sense of representation independent. If there isn't a logic for P, then P is different from NP. So there is a fundamental difference here. I mean, if there is no logic for P, then there is a fundamental difference between P and NP, and this is, after all, what we want to understand. What is the difference between the two classes? So what I would say then is that studying this problem, actually, I'm not saying it's going to yield insights on the P versus NP problem and not solve it, definitely, but I think it's a fundamental question that we need to understand. What is about the non-determinism that allows for a logic that P doesn't have? All right. And the last motivation for this problem would be that on the way to trying to attack it, there has been many new insights, and one of them is the one that I want to introduce now, which is how to extend fixed point logics, and first order logic by some counting mechanism, and what does that lead to? Okay, so if the bottleneck seems to be counting, then let's add counting to the logic in a way that is representation independent, and then see what we get. And it turns out that we're going to get some connections with proof complexity, and this is the topic of the talk. All right, so this was my view of descriptive complexity. And so let's not, and that's it. I mean, let's now add this counting. It's still a bit of descriptive complexity because I want to introduce this logic. So what does it mean to add counting to your logic? Well, there is one possibility, which is you add counting quantifiers of the type there are at least I elements that satisfy a certain property phi of x. Right? The problem with this is that which I do you put here? If you have a single formula, then a single formula would have some bounded on number on this I don't know, some constant 25, and then you can perfectly express it with 25 variables, so there is no point. But we'll come back to this kind of quantifiers later. What the other method to introduce counting into the logic is by considering a two-sorted kind of logic. So I have two sorts. So on the one hand, we have the universe sort, which is just a set of vertices if we're talking about graphs, and the other one would be the counting sort, and this would be the numbers between 0 and the cardinality of the universe minus 1. So I have two sorts. Now the atomic formulas are going to be the sigma atoms as usual between universe sort on universe sort, and then we're going to have arithmetic on the counting sort. And arithmetic means linear order plus and times. And again, this is arithmetic on small numbers. Okay. All right. So these are the atomic formulas. Then you have the usual connectives. You have quantifiers. First order quantifiers for the universe sort, and also first order quantifiers for the counting sort. And I'm going to use the counting variables I instead of x. And then you need some way to connect one sort with the other, otherwise this is completely disconnected. And these are the counting terms. So the counting terms are just a new construct of terms that give you the number of x's that satisfy a certain formula x. So you have this as a new term in your language. And what this does is it counts the number of x's that satisfy the formula and returns, and it's a term that represents the element in the counting sort that has the number of elements that satisfy phi. All right. So this would be the framework for the logic. Let me erase this because for the moment it's not relevant. And now we can think of first order logic with counting is exactly this thing. You can think of inflationary fixed point logic plus counting, which would be exactly this thing plus the inflationary fixed point construct applied to the counting sort and the normal sort. So you have these two things. It's plus IFP. All right. So now at this moment, for example, this evenness of the universe is perfectly definable because you have arithmetic on the counting sort. So all you have to say is that, well, there is an element so that x plus x or I plus I equals the maximum. The maximum is definable because you have the linear order. So examples evenness. But also evenness of edges. By the way, here my counting terms count only single elements, but you could actually extend the logic to count also tuples, and that is definable actually. So you can count tuples of elements. Even though it's not in the universe, but you can consider tuples of elements like this to represent numbers, polynomial size numbers. Okay. So you can count the number of edges, which is up to n squared.
Does your IFP operator allow relations that include variables of both sorts?
Yes, yes, yeah. So this thing allows arithmetic on the counting sort.
But it allows you to have variables input to R that are of both sorts.
Yeah, everything is allowed. Yeah. In fact, all these things you're allowed to have also parameters of all kind. Yeah, just throw in everything. I mean, there's no risk here, and it's a very robust logic. All right, so here are some examples, evenness of universe, evenness of edges, and many others. For example, one that is very non-obvious is that, for example, perfect matching on bipartite graphs. This is a very non-trivial result due to Blas, Gurevich, and Shelah. So this is definable in inflationary fixed point plus counting. It's not definable in inflationary fixed point. Well, among other things, because perfect matchings would allow you to define cardinality constraints of the kind. even more, for example, a deep result by Martin Grohe shows that any polynomial time property of planar graphs is definable in inflationary fixed point plus counting. So this means that restricted to planar graphs, inflationary fixed point plus counting captures polynomial time. So restricted to planar graphs, you have that. And recently this has been extended to any class that excludes some minor. And this is Grohe 98, I believe, and this is Grohe last year or something like this. It's a century of difference. So this is a very deep result. It uses a lot of graph minor theory behind. All right, so it's saying that it captures a lot of very closely polynomial time, at least on classes that exclude some minor, and even more. For example, you could say there is it captures polynomial time, any polynomial time property on almost all graphs. So what this means is that any P property on a class structure of graphs of measure 1. And by this I mean asymptotic measure 1. So if you count the number of graphs of size n, it includes almost all as n goes to infinity. It's almost all graphs. So this is also true, right? So this means that this logic is quite close to capturing P, but it turns out that it doesn't. It doesn't capture P. A non-example would be, and actually this is quite non-trivial, a non-example would be the isomorphism of bounded degree graphs. This is due to Tsai, Führer, and Immermann in a deep result that I'm going to discuss a little bit more in a second. So the isomorphism of bounded degree graphs is decidable in polynomial time by Luke's algorithm, but it's not definable in this logic. And so it took a bit to find a property that is not definable in the logic. So, and the reason is that it's very expressive. So the question at this point is, how do you show that something is not definable in fixed point plus counting, and what is exactly the result of Tsai, Führer, Immermann? I want to discuss that in a moment. So let's discuss about, or at this point enters infinitary logic. Okay, so when you want to show that something is not definable in some logic, what you do is you show it's not definable in a stronger logic. Right? You make the problem more difficult and then you solve it. So, so infinitary logic has been used in many areas of logic, in model theory and other areas. And what it's used is to embed this logic, IFP and IFP plus counting. You embed them. This was FO is here, and FO plus counting is here. You embed them in the infinitary logic, which is called L omega infinity omega, and this one would be called C omega infinity omega. And what this logic means is that you have the usual sorts. I mean, it's one sorted logic. You have the sigma atoms. You have negation, infinitary conjunction, infinitary disjunction, and also the finitary ones, and the quantifier. And now the symbols here mean that this infinity is because it's infinitary logic. This omega is because you only allow, well, after all, there is only a constant sorry, not constant, a finite number of quantifiers in a row. And this omega is because what you restrict is your formulas. Since they are infinite, they could have infinitely many variables, but this omega restricts them to have finitely many variables only. So you have an infinitary formula that has only finitely many variables and finitely many quantifiers in a row. I mean, depth, quantifier depth. All right, so and this you stratify also usually, stratify like this. So this would be the logic where you restrict the number of variables to k. Now this logic was introduced by Barwise, and this logic was later once this counting was introduced. You can define it just the same as here with the counting sort, but alternatively you can define it by adding counting terms, saying that there are counting quantifiers, saying that there are these I elements satisfying phi for every I. And now at this point these counting quantifiers are useful because since the formula can be infinitary, you can have all natural numbers involved, and therefore you're talking about all sizes, not only up to some bound. Okay. Of course, this is expressible with I variables, and that means that you cannot just embed this one inside this one, because since you have k variables restricted, if you were using this I to be, for example, k plus 1, then you wouldn't be able to do it, right? So on the one hand, you add these counting quantifiers, but on the other, you restrict yourself to k variables in total. All right. So these are the logics that on which you embed these, and then define and then show non-expressibility in these logics. And the way non-expressibility is defined in these logics is through elementary equivalence in these logics. So you have this indistinguishability relation. So we're going to say that m and n are c, k, omega, infinity omega indistinguishable, even only if, take this definition, they satisfy the same properties of the logic. For every phi in c, k, infinity omega, m satisfies phi, even only if n satisfies phi. Okay, so this is elementary equivalence in the logic. We're talking about finite structures, but you could define it in general. And the point is that this thing is characterized by an Ehrenfeucht-Fréset game. So fact even only if well, you can characterize it by a system of partial isomorphism with a back and forth property, which is the same as winning strategy in the Ehrenfeucht-Fréset game. So duplicator wins the counting Ehrenfeucht-Fréset game with k pebbles. And the k pebbles here is important because we have this restriction on the number of variables. So what this means is that the Ehrenfeucht-Fréset game is played by putting pebbles on the structures. You can choose left or right, but you can only use up to, both spoiler and duplicator can use only up to k pebbles. And then, so this satisfies the usual rules of the game, where you have to preserve partial isomorphism, and then you have some counting moves. In the counting moves, so let me describe the counting game. Have m and n. So the usual moves, you put pebble here, duplicator replies with a pebble there, spoiler puts a pebble here, duplicator replies with a pebble there. In the counting move, spoiler chooses one of the structures and a set in that structure, say here is a set of points. Duplicator is required to choose the same cardinality on the other side, set of the same cardinality. Then spoiler puts a pebble inside the set on the right, and duplicator answers with pebble inside the set on the left. And once this is done, the sets are forgotten. The sets are forgotten, and the pebbles are left on the board. And you keep playing. So intuitively, this counting move, what it's doing is, spoiler is saying, I claim there is a certain number of elements satisfying a certain property. So I claim that these elements, all these elements here satisfy this property. And then asks the duplicator, what is your set on the other side? The duplicator says, here is my set. These are my elements. They have the same cardinality, and they satisfy the property I claim. And then spoiler says, I don't believe you. Here is a point I believe you're not going to be able to reply to. And duplicator does its best. Well, I claim that this is the one that corresponds. And then the game continues until spoiler finds a contradiction, finds a non-isomorphism. Okay, so this is the intuition behind this counting move. And it's a fact in the theorem that, that these two things are the same. So now if you want to show non-definability in ck infinity omega, what you have to do, so suppose you want to show that, I don't know, some property is not definable. What you would find, you would need to find two structures, one that satisfies the property, one that doesn't, and then show that duplicator has a winning strategy showing that these two things are indistinguishable. Because if this one has the property and this one doesn't, if it were definable, then the same formula would hold on both, which cannot be. Okay? So this is enough, and it's actually a complete method. If it's not definable, then you can always find such pair of structures. So this is the method of showing. Okay, so this is what Fourier-Immermann did.
That would be the isomorphism of bounded degree graphs. So M and N would be pairs of graphs.
What is the question? How to do the non-definability?
No. But the example for which you can show this, that would be pairs of
Pairs of
bounded
graphs,
degree.
yeah.
And bounded degree means what? So it's a fixed bound on the degree.
Three.
Or 3. Okay.
So this comes now in, actually I want to state the theorem because it's stronger than what I said. Okay, at this moment I'm not going to state it with pairs of graphs, but it's going to follow from this. So this is the theorem of Fourier-Immermann. It says that there is an epsilon. It's a very strong result of complexity type. It says the following: there is an epsilon such that for every large enough n, there are graphs Gn and Hn with n vertices, such that the maximum degree of Gn and Hn are subcubic, meaning maximum degree at most 3. Second, they are non-isomorphic. I'm not talking about just a pair of graphs, and just one pair of graphs for the moment, and they are indistinguishable. Oh, there should be some. They are indistinguishable. Yeah, this is correct. By C epsilon n infinity omega Hn. So they are indistinguishable not by ck infinity omega for a constant k, but they are indistinguishable by a linear number of pebbles, linear on the number of vertices. So it's a very strong indistinguishability result. Okay, and it's actually not difficult to describe this construction. It's based on some, the graphs here have to have, for example, they could be, the underlying graphs are based on expander graphs, and then you do some gadget replacement in a very clever way, and once you do, so they are based on the same graph. You have some expander graph G, and from these you do some gadget replacement. You get some G hat, and from these two you do G is just itself, and G hat is obtained by doing some local change in the graph. You get H. So you do some local change that is indistinguishable by the logic, and that makes the graphs non-isomorphic. All right, so this theorem has the consequence of non-definability of isomorphism. Isomorphism of subcubic graphs not in C omega infinity omega. And that's because what you do is you take a pair of graphs. On one side you take Gn Gn, and on the other hand you take Gn Hn. And it will turn out that this pair of graphs is indistinguishable by C epsilon n omega infinity and infinity omega logic. And that's because the strategy is composed. Here you have the same, you play the identity, and here you play the strategy here. These two are of course isomorphic, they are the same, these two are not isomorphic. Okay, so this gives you the definability.
Back.
Yes?
Just a question. Is the usual error for Frasse games capturing indistinguishability some logic or?
Yes, yes, yes. If you drop the counting moves, then you have here LK infinity omega, which is the one corresponding to a non-count. All right. All right, so now I need to move to the other topic. And and the way to motivate this is by the following. So if these two graphs are non-isomorphic, but this cannot be told by a property definable in this logic, then what certifies their non-isomorphism? They are not isomorphic, so there must be some certificate of non-isomorphism in some way. What certifies it? And so this leads to the notion of certificates of non-isomorphism. And from there to prove complexity, it's only one step. Okay, so the way I'm going to phrase isomorphism is by an integer linear program. So you know that, so let's say if you have a graph G, let's call AG its adjacency matrix, n by n. N by n matrices. Now, G and H are isomorphic if and only if the following happens. There is a permutation matrix such that if you apply this permutation to the matrix, the adjacency matrix of G, you get the adjacency matrix of H. If you look at it, this is exactly what isomorphism means. Now, permutation matrix is a matrix of zeros and ones where every row has exactly 1, 1, every column has exactly 1, 1. It turns out the permutation matrices you have that the transpose is its own inverse. That's just easy to check. And therefore, you can multiply through by P and you get a linear condition here. So there is a permutation matrix such that AGP equals PAH. Here, just multiply by, well, of course, just multiply by P. And now this is a linear condition on your unknown, which is P, and therefore you can phrase it as an integer program. And the integer program here would have the following equations. So you would have, well, this multiplication on your left, UV PVW equals to P UV VW, and this for vertices in G, and this for vertices in H, for U in G and W in H. And then you want to add also the permutation conditions. This over W, this over V. and then this is 0, 1. So this is an integer linear program that I'm going to call ILP of G and H. So now, as a certificate of non-isomorphism would be any proof that this thing is unsatisfiable on 0, 1 would be a certificate of non-isomorphism. So, and I wrote it as an integer linear program because I want to apply not symbolic proofs but algebraic proofs, and in particular semi-algebraic proofs. So I'm going to use now these semi-algebraic proof systems. And here we have, we're starting with some linear inequalities. And then we're going to have some inference rules that are going to be valid on 0, 1. The inference rules are going to be, first of all, you can throw in the following axioms. It's always the case that xi squared minus xi is non-negative. It's always the case that xi minus xi squared is non-negative. Actually, it's equal to 0 in both cases. Xi is at least 0. 1 minus xi is at least 0. So these are axioms. And there is another rule that you can combine, if you have polynomials, you can form their positive linear combination. So if you have P1 of x, and this is now a tuple of variables, Pmx, then you can get lambda P1x plus lambda m Pmx, as long as this is sound, as long as the lambdas are non-negative. And then there's going to be one more rule that I want to introduce, which is the multiplication rule. And this multiplication rule goes as follows. If you have one polynomial, which you already showed is non-negative, you can multiply it by multipliers of this kind. These are called extended monomials, non-negative, and this as long as I and j are disjoint, and they are subsets of 1 to n. Okay, so this is sound because we are living in the world of 0, 1, and therefore this is non-negative. So this gives you 3 sound rules, and now you can define the complexity of this proof system. Yes.
Sum of squares is non-negative, or
No, let's not throw it. You could have another one, which you could also add squares. For any polynomial. But I don't want to talk about this one. And now I'll define proof systems, and then I connect the two things, which is what you are all waiting for, I guess. What does one thing have to do with the other? Okay, so the proof systems now are this LS, and this stands for lowest driver, lowest and driver.
excuse me, one more thing. So lambdas are reals, right? Or natural numbers?
Yeah, reals, yeah. Or rationals. Okay, so lowest driver would be this proof system restricted to quadratic inequalities. Everywhere you can only use quadratic inequalities. So A, C, M restricted to degree most 2. And this it was not introduced this way by Lowas and Shriver, but it can be seen that it's the same, I believe. I mean, I've seen this in some lecture notes by Lowas, but I've also seen it in a paper by Pavel Putlak, where this is introduced as a proof system. Then there is another proof system that you can think of is these three things restricted to degree D. There's no reason why it should restrict to degree 2. And this was introduced at least, I've seen it at least once in a paper by Grigoriev, Hirsch, and Politècnica. And then there is another pair of proof systems that I want to talk about, which is the Sherali-Adams proof system. These are again two people, Sherali and Adams, where now you have the three rules, but you have some structural restriction. So you have A, C, and M with no restriction except that all M's should come before all C's. And then SAD would be the same, restricted to degree at most D. Okay. So it is not obvious that these proof systems are actually even complete, but they are. So I'm going to focus on these proof systems here of Sherali and Adams. So SAN, where n is the number of variables, underlying variables, is complete. If the original system is linear, I'm talking about linear, this is S. If S is linear.
What's SAN if it was SAD before? So it's the degree or number of variables?
Well, this is restriction to D degree.
So you restrict yourself to the degree, which is the number of variables in your system.
You don't need to go to degree n squared.
Well, but then there wasn't actually the number of variables, it was some kind of dimension. So the number of variables was n squared.
No, well, here I'm talking about, in general, forget about isomorphism. This is up to the n.
Okay.
So degree n is enough to get a complete proof system. And the other thing is that these things are increasing in power, of course. And this is not a surprising thing. But you can also find a connection between the levels of SAD and the levels of LS. But I don't want to enter into this. So this is a complete proof system, and then you can ask about what is the smallest degree that lets you refute the system of linear inequalities that you're interested in. And this is where the connection is going to come, connection with discounting logics. So here's the connection. So let's define K, C, I'm changing letters again, doesn't matter. Kc of G and H, these are two graphs on n vertices. We define this as the minimum degree, well, the minimum K, so that G and H are indistinguishable, are distinguishable, not indistinguishable, distinguishable in this infinitary logic. Okay. So eventually, this is at most n the number of vertices. Eventually,
Because it's at most n if they're not isomorphic. If they're isomorphic, there isn't anything.
you're right. So it's either n or infinity at most. And then you define this K Sherali-Adams, the H to be the minimum degree, such that this ILP of G and H has a refutation in SAK. By the way, I'm not talking about sizes of proofs, essentially because if you bound the degree, then the number of monomials is polynomial. Well, polynomial, I mean, exponential in the degree, but if for fixed degree is polynomial. And because of this restriction of having all m's before all c's, it actually gives you a polynomial size proof. So, but I'm not talking about it because I don't need it. So you have these two notions that look very different. So this, to me, surprising thing is the following theorem that we showed in joint work with Elitsa Maneva just this year. We showed that counting logic is at most it's rated by at most 1, necessarily at m1. So the two measures of complexity of how hard it is to distinguish, they are related by 1. So essentially they are the same. Okay. So this connects and I knew this was wrong. That's why I was checking my notes, because I always get it wrong. I mean, there are two possibilities, I always get the wrong one. All right, so one question is, it would be very nice to get rid of this +1 and then see that these two things are exactly the same. And this could be possible, but I just don't know how to do it. I only know how to do it for when they are degree 1, then they are all the same. But if the degree is bigger, I don't know. So at this point, I should say some intuition why this is true. And the idea is, well, you would imagine what it is, but to make it formal is actually quite difficult. So the idea would be that in proofs can be thought as a prover-adversary game of some sort. And on the other hand, this indistinguishability can be thought as an Ehrenfeld-Frese game. And both things are defined independently. But it turns out that you can define a winning strategy from one to the other, even though this is not completely direct. Okay. So the idea is that if you have k pebbles, well, it's a bit hard to say the idea. I want to focus more on the consequences of it. But let me just say that the way this is proved is by interpreting the proofs as some sort of prover-adversary game and relating them to the Ehrenfeld-Frese game. So I want to mention a couple of consequences before I finish that are unexpected to me, and some open problems that this raises. So one first consequence is that the feasibility of certain linear programs, now linear programs, not 0-1 programs, linear programs are preserved by indistinguishability in the logic, which is not something obvious. So we define a concept of k local LPs, so this is the definition. And I'm not going to say what it is, it's just a syntactic form that you give to your LP associated to some graph or some hypergraph or some structure of some kind. And instead of giving the definition, I'll give you some examples of what are k-local LPs. So for example, perfect matchings or matchings on bipartite graphs, if you write it as a linear program, this is 3 local. Max flow, if you write it as an integer program, which is also a linear program, is 3 local as well. And the maximum cut problem, which is an NP-complete problem in general, you can write a linear programming relaxation, and then there are places where this linear programming relaxation is exact. For example, on K5 minor free graphs, so the max cut linear relaxation on K5 minor free graphs is exact, and this is a very non-trivial result of non-trivial result, and this is 4 local. Vertex cover, yeah. Relaxation is 2 local, or 3, I don't remember, doesn't matter, it's small locality, etc. Okay. So one first consequence is that if one of these programs is for a given graph, if you have G and H that are indistinguishable in the locality thing, if this one has a certain optimum in this linear program, then this one has the same optimum. So feasibility and optimality is preserved through indistinguishability in the logic. So one consequence of this is that these problems are definable in the logic. In particular, for example, matching on bipartite graphs is definable in the logic. In which logic? In C3 infinity omega. Find matching on bipartite graphs. And this was known by this result of Blas, Gurevich, and Shelah, but this proof is completely different. Actually, they prove a slightly stronger thing because they do it in inflationary fixed point, and I only do it in C omega, in C infinity omega. But then also max flow is definable, and this generalizes the matching case, and all these cases are definable. For example, max cut on K5 minor free graphs is definable in the logic, which is something I wouldn't know how to do at all without that result there.
Presumably that also follows from Gruit's.
Well,
all polynomials then.
yeah, except that
Yeah,
he wouldn't get a 4, he would get a big constant here. All right, so these are consequences for finite model theory, and so I don't have time to mention other consequences for example, for integrality gap constructions. I'll just mention one open problem. Well, yeah, one open problem that entails 2 open problems. So the first question is, what is indistinguishability by LS degree 5? So I choose 5 just as a small constant. So you remember you have SA 5, right? So indistinguishability by SA5 corresponds to definability or indistinguishability by this logic. So the question is, what if you allow now Loba-Schreiber of degree 5? So what is indistinguishability in logic terms? So this one has a very clear characterization. What about this one? This is, I have no idea. Second question is, find 2 non-isomorphic graphs that are LS5 indistinguishable. And the claim is that the Tsai-Fourier-Zimmermann graphs do not work, are LS5 distinguishable.
The claim is what you can prove.
Yes. I can prove that the Tsai-Fourier-Zimmermann graphs are distinguishable in degree 5. So now the question is, could it be that this defines certificates for non-isomorphism for all graphs, or can we find non-isomorphic graphs that are LS5 indistinguishable? I leave this open and I finish here. Thank you.
As we went over time, I'd suggest that we take questions offline, or perhaps for the break which follows after the next talk.